Hi, we are from Team Resurrectors and we are here to present a final project, Access Control Router with Multi-Level Security. My colleagues are Jenny and Varun, who will be taking up the later part of this presentation. So let me just start off with what led us to, what motivated us to take up this project. So what you can see here on the screen is the spread of the code red virus in different stages of it. The yellow, as you can see, is the initial stages, and then the middle stage and the late stage. As you can see, it started off as a very small place, as a very small virus, but it spread so rapidly and it caused a lot of damage. Some of the statistics are there on the screen. It spread to around 400,000 PCs in about 14 hours. In its heyday, it was said to have infected about 2,000 new hosts every single minute. It caused a lot of widespread damages, almost $2.75, and it was most of it was just in cleanup. The code red virus was actually just a simple virus which was downloaded. You get a mail with an attachment in a Word, and if you open it, it got downloaded into your PC. And when that happened, the mails were sent out to all your contacts in your mail, and then they were infected in that way. So it has been, there was a research which was conducted by the University of Sydney, and which says that there are 6 new viruses which are created every day. So in this new age of telecom, we wanted to target something which would solve this problem for us, which would handle this problem which is growing very rapidly. So I'd like to present an application. I would just like to give you the application overview of what our solution is and how it works. So what we were targeting is a security solution which would not only it does not just consist of one layer but of 2 layers. The second layer would actually accentuate what the security is being provided by the first layer. So as you can see here, we have two internal nodes, node N0 and node N1, and then we have the internet at other end, and then here we have our gateway and NetFPGA router. So the node N0 is like a highly secure LAN, and the node N1 is like a private semi-secure LAN. So we basically divided our internal LAN into 2 parts. The highly secured LAN can be anything. For example, in a bank it can be like the customer database, and the semi-secure LAN can be anything ranging from the customers accessing the account or the employees of the bank accessing their account. So what we were targeting is a security application which would provide a greater deal of security to the highly secure LAN, while also providing security to the semi-secure LAN. One of the first steps in our application is exchanging RSA keys. As we all know that encrypting the data always increases or manifolds the security in a data. So we have integrated RSA into a system which is done completely in hardware. So what this basically does is we have one of the nodes sending its public key to the NetFPGA. The NetFPGA is going to process this data and then encrypt its own public key using the public key of the node which has sent it and send it back. The node in turn is going to encrypt the symmetry key using the FPGA's public key and going to send it back. So as we can see here, so I'm going to simulate it in a simple application overview. The node right now has sent its public key to the NetFPGA. Once the NetFPGA gets it, it is loaded into a FIFO. Once it loads into a FIFO, our CPU picks up the public key. It performs the encryption using the crypto engine hardware accelerator. It basically encrypts its own public key using the public key which the node has sent to it, and it is going to send out. As you can see here, there's a table which is generated. This table is inside a scratch memory in our FIFO. So we have a reconfigurable FIFO which is divided into 2 parts. So in this, we have a table in a scratch memory where we maintain a list of all the authenticated users. For example, we see here that node C has been authenticated. There are some other tables in the scratch memory. One of them which will be used later, which is used by the NAT and by the access control part. The NAT maintains a list of the private and the source and the destination IPs, and the access control also maintains a list of IPs to maintain a list of the transaction or the packet exchange which has occurred. Coming back to RSA, so once the CPU has picked up and done its operation, it is going to put its own public key, encrypted public key into the FIFO and send a packet back to the node. So the packet has, once that is done, the packet is sent back to the node, and the node is going to pick up that encrypted public key, decrypt it, and then using that he's going to encrypt his symmetric key and going to send it to the FPGA. So now I'm going to show it in a real-time environment as to how we achieve doing it. As we can see here, I have set up everything. I have programmed my FPGA board, and I have set all the, I've set up I programmed the FPGA board. I have the nodes N0 ready here, which is ready to send its public key. I have a TCP dump ready on the left hand side for N0, which shows once the key has been received. And this right here is my FPGA board control node. So here I'll be able to read out the data and show you once the keys has been received. So before I start off with the operation, I'm just going to log into my FPGA board and show you that the key has not been received yet. So I've logged into my, I've set up the connection to my FIFO memory right now, to my scratch memory basically. So I'm going to read the software registers. As you can see that there's nothing has been received yet because I've not initiated the connection. Public key, the public key, FPGA, the symmetric key, nothing has been received as of yet. So now I'm going to return back to my system. Okay, looks like we're all set to go. So now this has been done. We have scripts written or ready with us, which basically do all the key exchange for us. The one major thing which we'd like to note here is that everything is done in hardware. There is no software implementation or no decryption, encryption, nothing is done in software. The entire part is done completely and specifically in hardware. So I have a script here which is going to generate, which is going to send its public key to the FPGA. The FPGA is going to handle it, decrypt it, and then encrypt it and send it back, and then the node is going to send its symmetric key encrypted back to it. So once I do that, it starts off. So as you can see that I have sent, the first thing which does was the node sent its public key. The FPGA got it and then did some operation on it and then encrypted its own public key using that and then sent it back. The public key, the encrypted public key of FPGA is here. So it is 6F001C, it is this part. So, and once that is done, the node now has got the public key. It is going to decrypt that public key. It has encrypted the symmetric key which it has or it wants the FPGA to give and then sent it. The public key or the symmetric key which it sent is this one: 5FC8, 3B3F, 5FC8, and 7DF9, 7D49. So I can log back to my scratch memory to show that this has been registered in our table which I showed before. So if I read all the registers, as you can see, this is here. The public key received from the node is 7 and the received public key N is 253. The public key which the FPGA has or which wanted to send, the N was 221 and the E is 7. It encrypted it to the format 111 and E28 and sent it back. The node received it, decrypted it, and sent the symmetric key, which it sent the encrypted symmetric key. But once this got the encrypted symmetric key, it decrypted it back and received it in this format. The key which it was sent is this here, 5C83B3F, which is similar to this key here, and then it decrypted it to this format. So once this key has been received, now all the data which will be passing through our NetFPGA or our router to the nodes which have authenticated now, all the data through that will be encrypted using this particular 64-bit symmetric key.
Once the RSA authentication is done, it means that all the nodes which are supposed to be secure are all been authenticated inside the network, and they'll all be entertained within the network. So here let's see how are we going to handle the packets from private network to the internet and from internet to the private network. Again, within the private network, how are you going to handle the packets between highly secure network to semi-secure LAN or semi-secure LAN to highly secure LAN. Now initially, if the packet is being sent from highly secure LAN to the internet, how are we going to handle it? So this packet is sent to the NetFPGA first, and then it goes to the NetFPGA. Inside, what happens? It follows, it goes to the FIFO, it goes to the hardware accelerator, and it does some operation, and we are maintaining two tables which are the hardware tables, and it generates the data which will be used later for the stateful inspection. Here you can see this data is being sent from node N0 to the private port 2023, and for the external IP to 200.1.2.3, and for this destination port. Similarly for the second port, here you can see the same data is being recorded, because this is the second level of controlling that we are doing, and this would be irrelevant for the semi-controlled semi-secure LAN. And the packet goes out, and you can see that this is the packet destination and the packet source port and the destination port, and it goes to the internet. And when the packet comes back, as our NetFPGA does search inside the NAT table and the access control table, and it finds the match that the packet is coming from the same source that earlier that N0 sent, and it is the same destination port and it is the same source port. So that packet is actually genuine. It will be routed to the highly secured LAN. Then what if some unwanted packet from internet tries to enter our internal node? So what happens? So it comes to the NetFPGA, and NetFPGA searches the parallel search inside the access table and the NAT table. It finds that there is no match, and it routes to some other node. Similarly, if some unwanted packet which is coming from semi-secure LAN which is already affected, if it tries to enter the highly secure LAN, again it finds that there is no match because there is no initiation of packet from highly secure LAN, and it rejects the packet. So now let's go with a small demo. Practically, how does it happen? So here I have set up a setup which has the TCP dump running on N0, and this is N2, and this is N3, and this is N0, and this is N3 again. So here the server traffic, this is the public node, which is the internet, which is ready to receive the packets which are being sent from N0, which is the internal node. So whenever the packet is being sent from N0 to the internet, so it will be translated to some other IP, which I'll be showing it later. So let's start the packet. So I'll be generating traffic from N0 to N3 with this script, and you can see that from here it will be packet which will be sent from N0 to N3, but here while on the receiving side the IP address would have been changed to some other IP. So as you can see here, so packets are being sent from N0 to N3 now, and here you can see this is the IP. It is sent from N0 to N3, but here on the receiving side you can see that it is actually receiving from N2, which is some other node, and this is the IP address. It says that 0A01 and 0003, this is what the sent IP, whereas here it is 0203. So this is the translation which is being done, and here on the now if packet from N3 will be sent to N0, and N0 will receive only if if it is sent from N3, and this is the destination port and this is the source port. So I have a script which will send a packet. So as you can see, this is the script. So now I am specifying which source port that I have to send it from. So here it says it is 44678. 44678. If I send it from this source port, it will be received in N0. As you can see, the packet is sent from N3 to N0, but here it is received from N3 to N0. So there is again a translation which is being done, and it passed 2 level of security. Now again, if I try to send with the same port, it won't accept. The reason is because it is already received, and one packet is already received. So, and the client has not yet initiated the process, and this is considered as a packet which is not good, which can be malicious. So this packet will be routed to N2, and here you can see that this packet will come here. See, and now onwards, whatever the packets that is sent from here will be sent to this. Even if we flood it, it will go here. Now I try to flood from N3 to N0, and all the packets will be going to N2 because it will not match any of the internal NAT tables. So I have a script which does that. So it simply floods the N node or N2, the router which is being exposed to the internet, and you can see that all the packets are being routed to N2 from N3 to N2, and this is how it avoids the problem for the N node if there is any malicious packet. And same thing happens with the N1 as well.
Let us now start with the second level of security that is provided by the access control. So as we had already seen that NAT is the first layer of security and access control is the second layer of security, where your highly secured LAN is secured from, it's prevented from any malicious packet which is going through if it's not intended. So here, as you can see, our node N1 is a semi-secured LAN and node N0 is your highly secured LAN. So unless N0 wants to communicate with some other nodes, that is, it initiates the communication, any packets which is received that is unwanted will be dropped, as in it's routed to some other node. And if N0 wants to communicate with N1, it sends up a packet for the communication, for the initiation of the communication, and in response the packet sent by N1 is received by N0. So this is all done by maintaining access table, where we are storing the IP addresses and the source and the destination ports, and this is being compared, and any unwanted packet can be identified and can be routed to a different destination. So let's see the demo for this, how we have implemented it in hardware. So here is setting up of different screens needed for this application. So this is your node N1 where and this is your node N0. So we'll show the communication which is happening between these two and how the unwanted packet is being routed to some other node. So here you can see it's set as server and this is we'll set as client, and now we see that the packet is received here, that is N1. We have used TCP dump. Similarly we can see it here. This is N0, so it's received from N0 to N1. Sent from N0 to N1, and similarly here you can see the response which is received from N1 to N0. So this is and the highly secured network has initiated the communication, so the packet is being received. So now we'll see if the communication is not initiated, that is any unwanted packet, how is it routed to some other node. So now you can see here I sent a packet from N1 to N0, but this was not initiated by N0. So as you can see, the packet didn't go through, and it went to the N2 port, N2 node. So this is where the unwanted packets are being routed to. So finally you can see how we have a highly secured network being established with 2 layers of security provided by NAT, and second one is provided by access control, and all this is done by comparison between different parameters taken into consideration. Thank you for watching our video. Have a great day.